So this video will discuss number 6 from the 2024 AP Calc BC free response set. And the BC test always has a series problem in position 6, and that is no different here. So they present us a Maclaurin series for the function f given by this function here. Converges to f of x for all x within the interval of convergence. And we also know that the radius of convergence for this relationship is 6. Determine whether the Maclaurin series for f converges or diverges at 6. Give a reason for your answer. So this is likely something you've done when you've determined that a radius of convergence is a finite value. You manually would plug in the endpoints to figure out if you can include either or both of them within the interval of convergence. In this case, they just ask us to consider 6. So when you put 6 in place of x, you do get some nice cancellation to occur, so the series becomes this. Now for this series, what can you do to determine whether it converges or diverges? It's not a geometric series or the harmonic series or a P series, a series that you would likely be able to look at and instantly know, hey, this converges or hey, this diverges. So you are going to have to go to one of your convergence tests. And anytime you have a series that possesses only positive terms, and from n equals 1 on to infinity, this series is only going to possess positive values, and it's a polynomial over a polynomial, I'm always going to go with some form of a comparison test. And the direct comparison test is sometimes inconclusive, so I usually opt right away to go with the limit comparison test. So for the limit comparison test, I do need my terms to be positive. We just said that that is the case as long as n is above 1. Should have an equal to sign here. And behaves like. What does this behave like? Well, when n gets big, this plus 1 in the numerator doesn't really have much effect on the numerator's value. So this behaves like n over n squared, which is equal to 1 over n for large values of n. Now, if you check the limit as you approach infinity of the series that you are trying to determine convergence or divergence of, divided by the one you're comparing with, so I went straight to multiplying by the reciprocal rather than dividing this fraction by 1 over n, I can simplify that limit to this, and through either L'Hopital's rule or using the quicker strategy when you're approaching infinity, polynomial divided by a polynomial, divide all pieces by the highest power of the variable from the denominator, you should end up with a limit of 1. Now what does the limit comparison test say as the conclusion? If your limit is positive and finite, so bigger than 0 and finite, whatever the series that you are comparing with does, and keep in mind we're comparing with the series that has this rule, 1 over n, your series is also going to do. So I don't think we've said this yet, but that series is the harmonic series, and the harmonic series diverges. Because this limit is positive and finite, the limit comparison test verifies that these series behave closely enough to one another that they do the same thing. So that tells us that the series that we are dealing with diverges when x equals 6. Part B says that f of negative 3 would be found by plugging negative 3 in place of this x in the series representation for f of x. Because the interval of the radius of convergence is 6, and this series is based at 0, negative 3 is definitely within that interval of convergence. So this will definitely equal f of negative 3, and they've simplified that for us to this. And it says the first 3 terms of this series sum to negative 125 over 144. Show that the difference between f of negative 3 and this third partial sum has an absolute value that's less than 1 over 50. Now hopefully you see this statement here at the end of part B and realize they're asking you to establish an error bound. And when you establish an error bound in a series problem, it's typically going to be one of two strategies, either using the Lagrange error bound or using the alternating series error bound. Alternating series is way easier. This is an alternating series, right? You can rewrite this as negative 1 to the n divided by 2 to the n. So we would have that negative 1 to the n representing our alternating term. So because this series, when negative 3 is in for x, is a converging alternating series, what we know is that the most error in estimating f of -3 with that third partial sum can be represented by the magnitude of the first omitted term. The first omitted term would correspond to the index value of 4. So if you put 4, and I'm going back to this version of the series, if you put 4 in place of the n's, so there's 3 n's to replace with 4, you end up with this. I ignored the negative. I guess you can do it for a variety of reasons here. Raising to an even power is going to give you a positive, but we only care about the magnitude of this term, right? We don't necessarily care about the direction of the error. We care about the magnitude of the error. Now, I do have to simplify this because it's asking me to show that this error is going to be smaller than 1 over 50. So if you think about what we've got going on in the numerator, it's 5 times 1, so numerator is pretty easy. This right here is 2 squared, and then this is 2 to the 4th in that denominator, so that's going to be 2 to the 8th total. 2 to the 8th is 256. 5 over 250 would reduce to 1 over 50. This is going to have a slightly smaller value than 1 over 50. Part C says find the general term for the Maclaurin series for f prime, the derivative of f, and then also find the radius of convergence for the series for f prime. When we take the derivative of this rule for the series for f of x, we get a Maclaurin series for f prime of x. So I'm literally taking the derivative of this, and this is a little intimidating the first few times that you see it done, but what's nice about taking the derivative of a series, you're taking the derivative with respect to x. You don't need a special rule for addition. You don't need a special rule for multiplication by a constant. And for this, you're simply going to apply a power rule. So I'm able to copy all of the addition, copy all of the constants in. Now you do see the inclusion of an n here, and that's from applying the power rule to this, right? Multiply by n, subtract 1 from the n. If you wanted to simplify this a little bit, you can. You'd get full credit for what's listed right here. I did cancel this n with one of the n's that was showing up down there. This is likely what's going to show up in the scoring guidelines once they post, but you would get credit for what's listed here. Now, it does say find the radius of convergence. Now, this word, I'm assuming most students would read that word and think, hey, I've got to use the ratio test to do this. That's what I do when I'm trying to figure out what the radius of convergence is for a Maclaurin series. There is a shortcut here. I'm going to explain the ratio test that I've set up, but if you know the radius of convergence for the series that converges to f is 6, you're still going to maintain that same radius of convergence for the one that converges to f prime. So there is a very quick way to get to the conclusion for part C, if you remember that relationship, but they didn't say state the radius of convergence, they said find the radius of convergence. So I think just the use of that word is probably going to push most students to using the ratio test. So you're taking the limit as you approach infinity of the absolute value of the next term divided by the current term. So you establish that ratio, you have the pretty frequently occurring cancellation occur within the ratio test. X and 6 do not change as n moves toward infinity. Now the x is going to have to remain in absolute values, but I can factor the x and the 6 out in front of the limit since the limit is only n approaching infinity. Like we argued in a previous portion of the problem, this limit can be done with L'Hopital's rule or dividing all terms by n squared. That's going to give you a result of 1 for this. So here is your result from the ratio test, absolute value of x over 6. Well, ratio test says we converge when that answer is less than 1. This answer is less than 1 when the absolute value of x is less than 6, which leads us to the same conclusion of a radius of 6. You don't have to do this, but I'm thinking that word's going to prompt most people toward that route. Last part of this says g of x is represented by this series. Use the ratio test to determine the radius of convergence for the Maclaurin series for g. So here they're flat out telling us to do the ratio test. So if we take the limit of the absolute value of the next term divided by the current term, and I went to multiplication by the reciprocal right away once again, we do have some cancellation occur. The cancellation is a little trickier here than it sometimes is. I have 2 extra factors of x in this numerator than I have down in this denominator. So that's going to leave me with an x squared up in the numerator. I have one extra factor of 3 down here than I have up here, I would want to try to distribute the n squared here, FOIL this out, multiply that in. So I've got what I don't have changing as n moves toward infinity factored out once again. I don't really need the absolute values around the x squared. X squared is going to be positive with or without the absolute values. The factor of 3 in the denominator can also be moved out. And then one more time, you have the opportunity to either apply L'Hopital's rule or divide by the highest power of n from the denominator to figure out that this limit is equal to 1. So 1 times what we factored out is just what we factored out. When does x squared over 3 satisfy being less than 1? Well, multiply both sides by 3, take a square root of both sides, and you end up with a radius of square root of 3.